A ship that accelerates at the same rate you feel in your chair right now could carry you to the edge of everything we can see in roughly 45 years of your own personal time. The entire observable universe before retirement age. That number is real physics, measured in laboratories and embedded in the satellites, guiding your navigation every day. The journey would pass the nearest star in 3 years and reach the galactic center in 20. Then, chapter by chapter, we tear it apart, because propellant chemistry, deep space radiation, dissolving bones, and fuel arithmetic that turns catastrophic near the speed of light all have something to say. If that is the kind of science you want, like and subscribe. We begin. Here is the most extraordinary number in physics, and it involves you personally. If you had a ship capable of maintaining a steady 1 gravity acceleration, the same gentle pull you feel standing on Earth right now, you could theoretically reach the edge of the observable universe before you retire. Every galaxy ever catalogued, every photon that has ever reached a human telescope, the entire 13.8 billion light-year span of everything we can see from here, crossed in roughly 45 years of your personal, biological, experience time. The whole universe in a career. That claim is true. It follows directly from equations that Albert Einstein wrote down in 1905 and that physicists have verified thousands of times since in laboratories and in orbit. The mathematics of special relativity, applied to a ship maintaining constant acceleration, produces this result with complete consistency. You could leave Earth at the age of 30, and if you kept accelerating, you would reach the far edge of everything humanity has ever seen by the time you were 75. The reason this has not happened, the reason no human has traveled farther than about 250,000 miles from Earth, is not that the physics is wrong. The physics is almost embarrassingly generous. The reason is everything else. The engineering, the biology, the fuel, the sheer brutal arithmetic of what it costs to push mass across cosmic distances. Physics says, go anywhere. Reality says, sit down. This is a story about the gap between those two things. That gap is not a polite academic disagreement between theoretical physicists and aerospace engineers. It is measured in magnitudes so large they resist ordinary intuition. The nearest star outside our own system sits about 25 trillion miles away. The fastest object humanity has ever launched, the Voyager 1 spacecraft, has been falling away from Earth since 1977, and at its current speed it would need approximately 73,000 years to cover that distance. Physics says the edge of the observable universe is 45 years away. Engineering has produced a spacecraft that needs 73,000 years to reach the nearest neighbor. Understanding how those two numbers can both be true simultaneously is the entire point of what follows. Along the way, this story will pass through an equation that a Russian schoolteacher wrote by candlelight in the 1890s, and that still governs every mission launched today. It will visit a real program, funded in 1958, designed to send families to Saturn and cancelled by a treaty, not by physics. It will run the arithmetic on matter-antimatter annihilation, the most energy-dense reaction in known physics, and reveal exactly why the most sophisticated particle accelerators on Earth have produced less of the substance than you could balance on the tip of a needle. Every propulsion concept here gets stress-tested against honest math. Every milestone gets checked against what actually happened, what actually worked, and what actually failed, because the history of human attempts to escape this planet is a long and specific record of the same collision between ambition and arithmetic, repeated in different forms across different decades. The 45-year claim is real. Every step toward understanding it will reveal why the distance between real and achievable is the most interesting problem our species has ever faced. But before any of that can matter, you have to fix what one lifetime actually means, and the answer is more specific and more unforgiving than most people expect. A lifetime sounds simple until you start counting what it actually contains. The average human life in the developed world runs about 80 years, from birth to death, but most of that span is consumed by things that have nothing to do with deep space transit. Childhood, adolescence, the early decades of adult life spent learning and building the infrastructure needed to function. A realistic window for an active deep space voyage, a period when the body is robust enough to endure the physical demands and the mission can actually operate, probably starts around age 30 and runs to around 65 or 70. Call that window 35 to 40 years in the optimistic case, perhaps 20 years in a realistic one, accounting for training, the logistics of reaching a departure point, and the plain fact that spaceflight is not wall-to-wall active travel from launch to destination. 20 years. That is the benchmark this entire story will measure every propulsion concept and every physics claim against. Can you get anywhere meaningful in 20 years? And if 20 years is too strict a standard, what does 80 years, your entire lifespan from birth to death, actually purchase if every one of those years were somehow spent in transit? The reason this framing matters is that the same physics equation produces very different answers depending on which clock you read. From the perspective of someone standing on Earth watching your ship accelerate away, a journey at near light speed takes essentially as long as the distance demands: years, centuries, millennia. From your perspective aboard the ship, traveling fast enough that time dilation compresses your experience time, the same journey might take a fraction of what the Earthside observer measures. The 45-year number from the opening chapter is measured in what physicists call proper time, the time on the traveler's own clock, in the traveler's own cells, beating through the traveler's own body. Earth might age billions of years while you age 45. That distinction will carry enormous weight later in this story. For now, the baseline is straightforward. The human body has a biological clock, and it runs whether you are accelerating toward Andromeda or sitting in a chair. Cells divide, bones lose density, radiation accumulates damage. The question of how far you can travel in a lifetime is, at its most fundamental level, a question about what the human body can survive and for how long before it fails. Humanity has been launching spacecraft since 1957. In that entire span, the farthest any human being physically traveled from Earth was roughly 250,000 miles to the Moon, achieved between 1969 and 1972 by 12 people, a record that has stood unbroken for more than 50 years. The farthest any object launched by humans has traveled is the current position of Voyager 1, sitting about 23 light hours from Earth. Impressive, given that it was launched in 1977. And yet, in cosmic terms, 23 light hours is essentially still in the driveway. The nearest star is approximately 4.24 light-years away. Voyager 1, traveling at 17 kilometers per second, would need 73,000 years to cover that distance. That is where we start. The record holder for pure speed does not improve the picture. It makes the scale of the problem even harder to look at directly. 17 kilometers per second sounds fast. At that speed, you could circle the entire Earth in under 40 minutes, fly from New York to Los Angeles in under 4 minutes, and reach the Moon in about 6 hours. Voyager 1, traveling at roughly that pace after more than 4 decades of flight, is the most distant human-made object ever built. A spacecraft the size of a small car, launched in 1977, now drifting silently through interstellar space beyond the edge of the heliosphere. At 17 kilometers per second, the trip to Proxima Centauri takes approximately 73,000 years. That number should settle into you. 73,000 years ago, our species had not yet developed agriculture. The last ice age had not ended. Cities, writing, recorded history, civilization itself, all of it came after. A Voyager-speed spacecraft aimed at Proxima Centauri would still be in transit when whatever replaces humanity has had 70,000 years to rise and collapse and leave no trace. The current speed record for any spacecraft belongs to the Parker Solar Probe, which made a series of increasingly close passes by our star and used gravitational acceleration to whip itself faster with each orbit. During its closest approach in late 2024, it reached approximately 192 kilometers per second, more than 11 times faster than Voyager 1. This is a genuine engineering triumph. At 192 kilometers per second, you cross the distance from Earth to the Moon in about 33 minutes. At that speed, a trip to Proxima Centauri takes approximately 6,600 years. 6,600 years is longer than the entire arc of recorded civilization. Every empire, every language, every technological leap from bronze tools to spacecraft compressed into a single journey that still has not arrived. Parker Solar Probe is more than 10 times faster than Voyager 1, and both numbers are equally, catastrophically insufficient for any mission a human being could survive, or any generation alive today could meaningfully plan for. There is something important in comparing those two numbers. Going 11 times faster when the gap is a factor of roughly 10 million is not meaningful progress toward interstellar travel. Speed improvements of 10 or even 100 times over our best technology change the trip duration from 73,000 years to 7,000 years. And both answers are indistinguishable from impossible when measured against a human lifetime. The deeper issue is how that speed record was achieved. Parker Solar Probe is fast because it fell close to our star and used gravitational pull as a slingshot, a technique that works beautifully in the inner solar system and cannot be repeated in the void between stars, where there are no massive bodies to borrow velocity from until you are nearly at your destination. Both our fastest and our most distant achievements tell the same story. The tools that got us this far have already reached their natural limits for this kind of problem. They are extraordinary within the solar system. They are completely irrelevant for anything beyond it. Something fundamentally different is required. And understanding why something fundamentally different is so difficult to build requires going back to an equation a Russian schoolteacher derived in a wooden cabin in the 1890s, without a laboratory, without colleagues, almost without anyone paying attention. His name was Konstantin Tsiolkovsky, and in 1897 he was teaching mathematics and physics to schoolchildren in a small town called Borovsk, Russia, working from a log house he had built himself. He was largely self-educated. He had almost entirely lost his hearing to scarlet fever as a child. He had almost no professional contacts in the scientific world, and in the quiet of that cabin, thinking about rocketry and space travel with the patience of a man who had no other outlet for his ideas, he derived a single equation that would govern every rocket ever built, including the ones carrying satellites into orbit right now. The equation connects three things: the change in velocity a rocket can achieve, the speed at which its exhaust leaves the engine, and the ratio of the rocket's starting mass to its ending mass. Written out, it looks deceptively compact. The mathematics contains something cruel, and the cruelty lives in the natural logarithm at its center. Here is what that logarithm means in practice. If you want your rocket to go twice as fast, you do not need twice as much fuel. You need exponentially more, and the fuel you add to go faster itself has mass, meaning it needs additional fuel to be carried, which itself has mass, which needs more fuel, in a spiral that collapses into absurdity long before you reach the velocities required for interstellar travel. To see this clearly, consider a simple benchmark. The best chemical rockets today, burning liquid hydrogen and liquid oxygen, achieve exhaust velocities around 4.4 kilometers per second. Getting from Earth's surface to low orbit requires roughly 9.4 kilometers per second of velocity change. Getting from orbit to Mars requires another 6 kilometers per second. A one-way mission to the outer solar system demands more than 20 kilometers per second depending on the route. Every unit of velocity you add requires an exponentially greater mass of fuel to start with. This is why the Saturn V rocket The largest launch vehicle ever successfully flown was approximately 96% fuel by mass at launch. The astronauts, the spacecraft, the life support, the science equipment, all of it together amounted to a small fraction, sitting atop an enormous column of propellant that would be gone before the first stage even separated. Tsiolkovsky saw this clearly more than a century before Saturn V flew. He understood that chemical energy stored in molecular bonds has an absolute ceiling. You cannot burn hydrogen and oxygen hotter than the physics of combustion allows, and that ceiling directly limits exhaust velocity, which directly limits everything else. The only escape from this tyranny was to improve exhaust velocity, because the logarithm punishes mass ratios but rewards faster exhaust. If your exhaust moves faster, you need far less of it to achieve the same velocity change. This single insight points directly toward every propulsion concept more advanced than a chemical rocket. Each step up the ladder is, in its essence, a strategy for squeezing more speed from the exhaust. Some of those strategies work remarkably well, at least on paper. Others run straight into physics problems that make chemical limitations look mild by comparison. The first step up that ladder starts with fire itself, and it reveals exactly how hard the ceiling really is. The most powerful chemical rocket ever built lifted off for the first time in November 1967. The Saturn V stood 111 meters tall, nearly the height of a 36-story building, and at liftoff it produced approximately 7.6 million pounds of thrust, burning liquid oxygen and refined kerosene in its 5 first-stage engines, at a rate of roughly 15 tons of propellant per second. It was, and remains, the largest functional rocket in history, designed in part by a team led by Wernher von Braun, built under deadline pressure from a program spending roughly 4% of the entire United States federal budget at its peak. The Saturn V was 96% fuel by mass at launch. 4% of its enormous bulk was structure, engines, payload, crew, and everything else. The rest was propellant, burned away in stages over the first minutes of flight. That ratio is not a design flaw, it is the rocket equation at work. The engineers who built Saturn V were extraordinarily skilled, and they extracted essentially everything the chemistry allowed. The specific impulse for the upper stage engines burning liquid hydrogen and liquid oxygen reached about 450 seconds, close to the practical ceiling for chemical combustion at any scale. That ceiling is set by temperature. The reaction between hydrogen and oxygen produces a flame around 3,500 to 3,600 Kelvin, hot enough to melt most metals on contact, requiring actively cooled engine walls just to survive the burn. The exhaust velocity that results from that temperature is what it is. No engineering can raise the flame temperature beyond what the chemistry allows. No materials breakthrough changes the energy stored in a hydrogen-oxygen bond. Now apply this to the problem of reaching the nearest star. A chemical rocket mission to Proxima Centauri, one way, not even bothering to slow down at the destination, would require achieving a velocity of at least a few percent of the speed of light to arrive in anything resembling a reasonable time frame. At 4.4 kilometers per second of exhaust velocity, the Tsiolkovsky equation calculates the required fuel-to-payload mass ratio for that velocity, and the number it produces is larger than the mass of every planet in the solar system combined. There is simply not enough matter in the nearby solar system to build the fuel tank a chemical rocket would need. Some engineers have proposed variants, staging rockets so that each successive stage starts lighter, clustering engines for extra thrust, using more exotic fuels. Every one of these approaches helps at the margins and fails at the scale. Staging reduces the mass ratio problem but multiplies complexity and cost. More exotic chemical combinations yield modest improvements in exhaust velocity, nowhere near enough to change the fundamental arithmetic. The wall is not made of engineering limitations. It is made of chemistry, and chemistry runs out of room long before the numbers become acceptable. Chemical rockets are finished as interstellar technology. They are extraordinary for reaching orbit, for sending probes through the solar system, for landing humans on the moon. For anything beyond, they hit a wall built directly into the structure of molecular chemistry, and no amount of engineering refinement will move that wall. The next step up the ladder does not explode anything at all. Dawn was launched in September 2007, and over the next 11 years, it became the most well-traveled spacecraft in history by total velocity change accumulated. It visited asteroid Vesta, orbited it for 14 months, then left and traveled to dwarf planet Ceres, the first spacecraft ever to orbit two separate bodies beyond the Moon, and it did all of this on a propellant tank of xenon gas that would fit comfortably in the back of a small car. Dawn's 3 ion engines worked by using electricity to accelerate xenon atoms to high speeds and shoot them out the back. The exhaust velocity was roughly 30 kilometers per second, almost 7 times faster than the best chemical rocket engines. Because of that higher exhaust velocity, the Tsiolkovsky equation becomes far kinder. The same velocity change requires a dramatically smaller mass of propellant. Over the course of its 11-year mission, Dawn accumulated a total velocity change of approximately 11.5 kilometers per second, using only 425 kilograms of xenon. A chemical mission covering those same destinations would have required enormously more propellant. The catch becomes immediately obvious when you look at how much thrust those engines produced. At peak operation, Dawn's ion engines generated about 90 millinewtons of force combined. To feel what that means, a single sheet of paper resting on a scale exerts roughly the same gravitational force. Dawn's entire propulsion system, running at full power, was pushing with the force of a few sheets of paper. That is why an ion drive mission covering billions of miles requires years to do so. The acceleration is genuinely tiny, measurable in thousandths of a meter per second per day. A European Space Agency lunar mission in 2002-3 demonstrated the same dynamic on a smaller scale using a Hall thruster, a variant of ion propulsion with slightly lower efficiency but higher thrust for its size. The probe took 14 months to complete a journey the Apollo missions did in 3 days, burning only about 80 kilograms of xenon, a fraction of what any chemical approach would have required. Ion drives are now standard hardware on commercial satellites. SpaceX uses Hall thrusters on every Starlink satellite for orbit maintenance. They work reliably, are well understood, and are genuinely superior to chemical rockets for missions where time is available and payload mass needs to be minimized. For robotic probes exploring the outer solar system, they are close to ideal. For pushing people to another star in a human lifetime, they fall short by many orders of magnitude. A crewed ship masses thousands of times more than Dawn. Thrust measured in millinewtons cannot accelerate thousands of tons to meaningful velocity on any timescale a human planner could accept. The efficiency advantage that makes ion drives brilliant for small probes becomes irrelevant when you try to scale to a vehicle that must sustain human life for years. The math here is simply prohibitive. Ion drives represent the upper limit of what patient electric propulsion can achieve, and that limit falls far short of where the story needs to go. But there is a propulsion concept that needs no fuel whatsoever, that has already flown in space, and that works exactly as its designers predicted. The catch is where its power comes from. In May 2010, the Japan Aerospace Exploration Agency launched a spacecraft named after Icarus toward Venus, and it carried something no spacecraft had ever successfully deployed in deep space before: a solar sail. 14 meters on each side, 200 square meters of ultra-thin aluminized polyamide film unfurled from a spinning drum in the void between Earth and Venus. No engine, no exhaust, no propellant of any kind, just light from our star. Photons carry momentum. When they strike a reflective surface and bounce back, they transfer twice their momentum to the sail. The force per photon is infinitesimal, but starlight delivers approximately 100 million billion photons per second per square centimeter at Earth's distance from our star. Add all of those tiny nudges together across a large enough sail, and you get measurable, continuous thrust. The sail measured a photon-induced acceleration of about 0.04 millimeters per second squared, generating thrust of roughly 1 millinewton. It worked. The sail deployed cleanly, attitude control was demonstrated, and the spacecraft went on to complete its Venus flyby mission, spending over a year in interplanetary space under pure photon propulsion. The Planetary Society's LightSail 2 mission, launched in June 2019 aboard a CubeSat small enough to hold in both hands, raised its own orbit around Earth for months using nothing but radiation pressure from our star. The mission ended in November 2022, when increasing atmospheric drag at low altitude finally overcame the sail's thrust. The sail had performed exactly as designed until atmospheric physics ended the mission. Solar sails are not science fiction. They are demonstrated flight hardware with real mission heritage and verified performance numbers. 2 separate spacecraft on 2 separate missions in 2 different decades proved that photon propulsion works in the real world. The underlying physics is also the most reliable in all of spaceflight. Our star will not run out of photons, the fuel mass is exactly 0, and maintenance is essentially non-existent for a sail with no moving parts. For a small probe that needs years to accumulate velocity and has no deadline, the appeal is obvious. The limitations surface immediately when you push the concept toward interstellar ambitions. Light pressure falls off as the square of the distance from the star. At Jupiter's distance, starlight exerts 25 times less pressure than at Earth. Beyond the outer planets, solar sails lose their driving force almost entirely. More critically, a solar sail has no way to brake at its destination. It can only be pushed away from a light source, never pulled toward one. Arriving anywhere at useful speed requires either a laser at the destination, a secondary propulsion system, or accepting that the mission is a one-way flyby with no stopping. The braking problem is not trivial. A spacecraft that has been accelerating away from the inner solar system for years arrives at its destination moving extremely fast with nothing to slow it down. Dropping into orbit around another world or landing on a distant moon would require decelerating against that momentum by some other means. An ion thruster could handle this, but then you have carried the propellant mass that solar sails were supposed to eliminate. A combination architecture solves one problem while recreating another. Every solution in spaceflight has this character. The constraints do not disappear, they migrate. Scaling a sail to push meaningful mass at meaningful speed requires something far more powerful than starlight. What it requires is a laser so intense that its output equals 100 large power plants, focused over millions of kilometers. That idea is real, funded, and being actively engineered, but it can only work for something weighing about as much as a few paper clips. Between 1955 and 1972, the American Space Agency and the United States Atomic Energy Commission ran the most comprehensive nuclear propulsion test program in history at a remote site in the Nevada desert called Jackass Flats. They built and tested 20 reactor and engine systems under a program called the Nuclear Engine for Rocket Vehicle Application. The concept was straightforward. Instead of burning fuel to generate heat, use a nuclear fission reactor to heat liquid hydrogen to temperatures far beyond what any combustion chamber could produce. Then expel the hydrogen through a nozzle as thrust. Hydrogen is the lightest element, which means it exits the nozzle very fast for a given temperature, and temperature is what determines exhaust velocity. A nuclear reactor can heat hydrogen to temperatures roughly twice what chemical combustion allows. The result was that the program's nuclear engines achieved specific impulses between 825 and 870 seconds, nearly twice the 450 seconds of the best chemical engines. Under the Tsiolkovsky equation, twice the specific impulse means dramatically less fuel required for the same velocity change, which means shorter missions, larger payloads, or both. The program's flagship engine, the experimental engine designated XE Prime, demonstrated sustained operation for over 90 minutes at full thrust in 1969. delivering 333 kilonewtons of force. It was a full-scale, flight-ready engine that ran successfully and met its performance targets. A nuclear thermal rocket using this engine could have cut a crewed Mars transit from 9 months to roughly 4 months, dramatically reducing radiation exposure for the crew. Missions to Jupiter's moons, which require years with chemical propulsion, would become genuinely practical. Then the Apollo program wound down. The agency's budget was slashed, and in 1972 the entire program was cancelled, not because the technology had failed, but because there was no longer a mission that needed it. The engines that worked were put in storage, the test facilities shut down, the institutional knowledge dispersed. In January 2023, the American Space Agency and the Defense Advanced Research Projects Agency jointly announced a new nuclear thermal demonstration program, targeting a flight demonstration as early as 2027. It was announced with fanfare and real institutional weight behind it. 2 years later, in 2025, the Defense Advanced Research Projects Agency cancelled its participation. The Space Agency's budget request for 2026 listed the program as terminated with zero funding. The Senate Appropriations Committee pushed back, directing at least $110 million toward nuclear propulsion regardless, and the outcome remains unresolved as of early 2026. A report by former Space Agency Associate Administrator Bhavya Lal and engineer Roger Myers documented the pattern bluntly. The United States has spent nearly $20 billion in constant year dollars on space nuclear programs over the decades, cancelling each effort before a system ever flew, and the conclusion was that the country failed to deploy them because of missing mission clarity and institutional coherence, not missing physics or funding. The same engine that worked in 1969 still works on paper today. The political story surrounding it keeps ending the same way, 60 years apart, and even nuclear thermal propulsion, as genuinely capable as it is, cannot close the interstellar gap. For that, something with far more violence in it was needed. Someone actually designed it. For 7 years, they built it on paper and metal and tested its key components, and they believed with good reason that it would work. In 1958, a physicist named Freeman Dyson took a year's leave from the Institute for Advanced Study in Princeton, where he had worked alongside some of the greatest minds in 20th century physics, and went to San Diego to design a spacecraft powered by nuclear explosions. He was not alone. The project's other driving figure was Ted Taylor, a brilliant weapons designer from Los Alamos, who had engineered both some of the smallest and some of the most powerful nuclear devices ever built. Together, under a program called Project Orion, run by General Atomics, they and their team spent 7 years working through the most audacious propulsion concept in the history of spaceflight. The idea was elegant in its violence. The spacecraft would carry hundreds of small nuclear bombs in its belly. At regular intervals, a bomb would be ejected from the rear of the ship and detonated about 60 meters back. The explosion would drive a wave of superheated plasma into a thick steel pusher plate mounted at the ship's tail. Between the pusher plate and the crew compartment, a system of large shock absorbers would smooth the repeated impulses into something survivable, a series of hard pushes rather than a single crushing blow. Detonate the bombs fast enough, and the acceleration becomes nearly continuous. The team wanted to know whether a pusher plate could actually survive repeated nuclear detonations at close range. They ran a test at Eniwetok Atoll. A 20-kiloton nuclear device detonated 10 meters from 2 steel spheres, each about a meter in diameter and coated with graphite. The spheres were recovered 2 kilometers away, with their interiors completely intact and only a few tens of micrometers of graphite ablated from their surfaces. The pusher plate concept worked. The performance numbers Project Orion calculated were extraordinary. Specific impulse ranged from 3,000 to 10,000 seconds, depending on the bomb design and plate geometry. A spacecraft propelled this way could reach velocities between 3 and 10% of the speed of light, speeds at which Proxima Centauri becomes a journey of 40 to 140 years, compared to 73,000 for Voyager 1. The team's internal motto was Saturn by 1970. This was before any human had reached orbit. They were planning family expeditions to the outer solar system using a ship they believed could be built with the technology of the 1950s. Based on the physics, they were right. Dyson's designs ranged in scale from a 4,000-ton vessel that could carry a crew of 20 to a concept he called the Super Orion, a ship displacing 8 million tons, roughly the size of a small city, capable of carrying 1,000 people on a multi-generational voyage. It would have been the largest structure humanity ever built. The detonation rate on that ship was about 1 bomb per second. The exhaust plume would have been visible from the ground. No other propulsion concept developed before or since has matched Orion's projected performance using only known physics and existing materials, without requiring breakthroughs in science that have not yet occurred. It was real engineering on real hardware, with verified subcomponents and a team of serious physicists who believed in it. And then something happened that had nothing to do with whether the ship could fly. In August 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Nuclear Test Ban Treaty. The treaty prohibited nuclear detonations in the atmosphere, underwater, and in outer space. Project Orion required nuclear detonations in or near the atmosphere for a ground launch and in outer space for propulsion. Both were now illegal under international law. Freeman Dyson had already been wrestling with this problem before the treaty was signed. He ran the numbers on what an atmospheric launch would mean for global radiation levels. His estimate, each launch would spread fallout, roughly equivalent to about 1% of all the nuclear tests already conducted above ground at that time, meaning perhaps 10 additional deaths from cancer globally per launch. He initially argued to colleagues that this was an acceptable price to pay for opening the solar system. It was a genuine moral argument, not a casual dismissal. He believed the long-term benefits of expanding humanity's reach would justify the short-term harm. Then he thought harder about what normalizing nuclear explosions as a transportation method would actually mean for the Texas world. If the United States launched atomic bombs through the atmosphere and called it space exploration, the door it opened could not be closed. Other nations would follow. The precedent would outlast any particular mission. He testified before the Senate in 1963 in support of the Test Ban Treaty, and by then, Project Orion's fate was already clear regardless. Official cancellation came in December 1964. Total expenditure over 7 years of serious engineering, approximately $11 million. For context, the agency's budget in 1964 alone was roughly $5 billion. Project Orion cost less than a rounding error in that year's space program, and it was the one concept that might have actually reached the outer solar system within human timescales. The physics that made Orion work has not changed since 1964. The treaties that stopped it remain in force. Modified versions of the concept, Project Daedalus in the 1970s and Project Icarus in the 2000s, explored whether a ship assembled and launched from orbit rather than from the ground might technically operate outside the treaty's scope. The geopolitical barriers are a separate and formidable problem. Nothing has flown. Project Orion stands as the only propulsion technology in history that could plausibly push substantial human-rated mass to several percent of light speed using materials and physics we already understand, cancelled by a treaty that was morally correct to sign and devastating to space ambition simultaneously. Everything that might exceed its performance relies on a process we have only recently begun to tame in a laboratory. And even that achievement came with enormous caveats about how far the engineering still has to travel. The figures around Orion spent the rest of their careers in the shadow of what might have been. Ted Taylor moved to nuclear non-proliferation work, haunted by what nuclear weapons had become. Dyson wrote and lectured about space for decades and never stopped believing that nuclear pulse propulsion would eventually be revived, perhaps by a civilization with fewer constraints than ours, perhaps in orbit beyond the reach of any treaty. He died in 2020 without seeing it. The filing cabinets with the detailed engineering drawings are still somewhere in a government archive. The physics is unchanged. On the 5th of December 2022, physicists at the National Ignition Facility at Lawrence Livermore National Laboratory in California fired 192 laser beams at a pellet of hydrogen fuel about the size of a peppercorn. The pellet was compressed by the laser pulse to temperatures and pressures comparable to the interior of a star. For a brief instant, hydrogen atoms were forced close enough together that they fused. When they did, the resulting fusion energy released was greater than the laser energy delivered to the target, more energy out than energy in. For the first time in the history of controlled fusion research, ignition, the headlines called it a breakthrough. Physicists called it a milestone. Both were right, and both understated how large the remaining gap still is. The laser energy delivered to the pellet was about 2.05 megajoules. The fusion energy released was about 3.15 megajoules. The lasers themselves required about 300 megajoules of electrical energy to fire, meaning the system as a whole was still deeply energy negative when measured from the wall socket. The gain was scientifically real, and demonstrating that ignition works at laboratory scale is genuinely significant. The gap between that demonstration and a sustained, net positive fusion power plant is still enormous. The gap between a fusion power plant and a fusion rocket engine is larger still. Fusion propulsion works by using the energy released in fusion reactions to heat and accelerate a propellant to exhaust velocities far beyond what nuclear, thermal, or chemical propulsion can achieve. A well-designed fusion drive could reach specific impulses measured in the tens of thousands to hundreds of thousands of seconds, and push exhaust at speeds representing meaningful fractions of light speed. The fuel, isotopes of hydrogen, is abundant throughout the universe and vastly more energy-dense than any fission fuel. A fusion rocket would, in principle, represent the first propulsion technology capable of reaching another star on a timescale that a human being could actually experience. Several private companies are pursuing fusion propulsion concepts. Helicity Space is developing a plasma-based approach targeting specific impulses of 10,000 to 20,000 seconds. The Limitless Space Institute funds university research across multiple advanced propulsion approaches at institutions, including the Massachusetts Institute of Technology and Caltech. None of these efforts have demonstrated net positive fusion energy in any form, let alone propulsion applications. The National Ignition Facility result used inertial confinement fusion, triggered by lasers, a completely different physical approach from what a compact shipboard reactor would require. The honest assessment is this: the physics of nuclear fusion is not in doubt, and the National Ignition Facility result confirmed that the basic process can be made to work in a human-built device. The engineering of a sustained, compact, net-positive fusion reactor does not yet exist anywhere on Earth. The engineering of converting such a reactor into a propulsion system is a further step beyond that. The timeline from first ignition milestone to a working fusion rocket engine is measured in decades at minimum, assuming sustained investment and no major unforeseen barriers. But fusion matters beyond its performance numbers. Of all the technologies on any realistic roadmap to the stars, it is the first one where the barrier is engineering difficulty rather than fundamental physical impossibility. And that distinction matters because the next technology on the list crosses a different kind of threshold entirely, one where the physics is perfect and the production problem is not a matter of difficulty, but of arithmetic that borders on the impossible. Matter-antimatter annihilation is the most violent reaction in known physics. When a particle of matter meets its antimatter twin, both of them cease to exist entirely, converting 100% of their combined mass into pure energy. Every other energy-releasing process in the universe is partial. Chemical combustion releases a fraction of a percent of its fuel's mass energy. Nuclear fission releases about 1/10%. Fusion does slightly better, but still releases only a few tenths of a percent. Antimatter annihilation wastes nothing at all. 1 gram of antihydrogen meeting, 1 gram of ordinary hydrogen releases roughly 90 terajoules of energy, the equivalent of a large nuclear warhead, from 2 grams of material that you could hold on the tip of a finger. A rocket engine running on matter-antimatter annihilation would be the most efficient machine our species could physically build. The exhaust from a well-designed antimatter engine would approach light speed, and the Tsiolkovsky equation responds extraordinarily generously to exhaust velocities near the speed of light. With perfect antimatter propulsion, the fuel-to-payload ratios that reduced every previous propulsion concept to absurdity become manageable. A round trip to the nearest star, accelerating and decelerating in a way that keeps the crew alive, would require a fuel-to-payload ratio in the range of roughly 30 to 40 for a perfect system. Demanding, but physically conceivable in a way that chemical numbers are not. The theoretical performance is so good that antimatter propulsion is the one technology that could actually deliver on the 45-year claim from the note opening chapter, at least in principle. Specific impulse in the range of tens of millions of seconds. Exhaust velocities close enough to light speed that the relativistic equations begin to dominate the calculation. If you could build a working antimatter rocket and fuel it adequately, the solar system would become an afternoon's commute, and nearby stars a realistic destination within a human lifetime. Here is where the arithmetic turns savage. Every particle accelerator on Earth that produces antimatter does so by smashing high-energy protons into a metal target with enough force to create particle-antiparticle pairs in the debris. Roughly 4 antiproton-proton pairs emerge for every million collisions. The antiprotons are then slowed, cooled, captured in magnetic traps, and used for physics experiments. The entire global scientific infrastructure devoted to antimatter research, running continuously for decades, has produced a combined total of less than 20 nanograms, 20 billionths of a gram. The full output of every antimatter-producing facility humanity has ever built, accumulated over all time, would be invisible without a microscope. At the best production rates currently achievable, manufacturing a single gram of antimatter would require approximately 30 billion years of continuous operation. 30 billion years is more than twice the age of the universe. The cost of that gram, calculated against the electricity and equipment required, exceeds 1 trillion euros. Those are not estimates designed to be pessimistic. They follow directly from the measured production efficiencies of real machines. The gap between what a working antimatter rocket would need and what we can produce is one of the largest numerical gaps in all of applied physics. The storage problem is equally formidable. Antiparticles cannot touch any normal matter container without annihilating. They must be suspended in magnetic and electric fields inside near-perfect vacuums, held away from every wall and every gas molecule. Storing a handful of antihydrogen atoms for 1,000 seconds was a world record when researchers at the European Organization for Nuclear Research accomplished it in 2011. Scaling from hundreds of atoms to kilograms is a problem for which no theoretical pathway currently exists. Antimatter propulsion is the best solution physics could possibly offer for interstellar travel on human timescales. It is also a solution that requires either a completely different method of production that does not yet exist, even as a concept, or a civilization with energy resources several orders of magnitude beyond anything we currently possess. For the foreseeable future, it lives in the same category as wishes. And yet, that same gap between dream and reality has inspired the most creative engineering concept currently operating in the real world. One that does not need antimatter at all, and has already secured $100 million in funding toward an actual flight. The idea behind Breakthrough Starshot is simple enough to explain in 2 sentences. Fire a laser array equivalent to 100 large power plants at a reflective sail the size of a kitchen table for 10 minutes, accelerating a sensor package lighter than a letter to 20% of the speed of light, and let it fly to Alpha Centauri on its own momentum. 20 years after launch, the probe arrives. 4 years after that, the first signal comes back. The simplicity of the description does not survive contact with the engineering. Yuri Milner announced the project in April 2016 with an initial commitment of $100 million, a scientific board that included Stephen Hawking, and a target velocity that would have made every previous space mission look stationary by comparison. 60,000 kilometers per second, 1/5 of the speed of light. A probe traveling that fast would cross the entire distance from Earth to the Moon in about 6 seconds. The laser array required to achieve this is a system unlike anything humanity has ever attempted to build. 100 gigawatts of coherent optical power must be focused by a phased array spanning kilometers, maintained in precise alignment across atmospheric turbulence, and fired in a sustained burst. A 2018 engineering study by Kevin Parkin estimated the capital cost of the ground-based beam director at $8.3 billion, with a per-launch energy cost of approximately $7 million per probe. Research published by teams at the Australian National University in 2025 confirmed that coherent combination of an array of millions of individual lasers is theoretically achievable with current photonic technology, scaled up enormously, but demonstrated only small-scale systems. The full array does not yet exist at any scale that resembles what the mission requires. The sail itself presents a different class of problem. A 4 by 4 meter sheet of material must survive illumination at gigawatts per square meter of laser intensity for 10 minutes without vaporizing, reflecting enough light to generate the acceleration required while absorbing almost none. Silicon hydride is the leading candidate material. Current prototypes are measured in millimeters to centimeters. Scaling to meters is an engineering problem without a current solution. Communication from Alpha Centauri adds another layer. The entire probe weighs a few grams. Transmitting a detectable signal across 4 light-years from an antenna that weighs grams, using a power source that also weighs grams, is one of the most demanding communication challenges in the history of electronics. The signal would arrive at Earth 4 years after the probe's flyby, 24 years after launch, and the information it contains would be whatever a gram-scale camera array could capture during a high-speed pass through a neighboring star system. Every one of those problems is a genuine engineering challenge, not a fundamental physics barrier. That distinction places Breakthrough Starshot in a different category from antimatter propulsion. The physics are not in doubt. The engineering is hard and currently unsolved, but there is no law of nature preventing a solution. The timeline to an actual launch is measured in decades, and the mission is a flyby for a probe the weight of a paperclip. The gap between Breakthrough, Starshot, and a crewed interstellar mission is so vast, it almost cannot be stated. A crewed ship masses millions of times more than a gram-scale probe. The laser power required to push it to comparable velocity scales with mass. A crewed ship must decelerate at the destination, which a laser sail cannot do on its own. All of the biological and psychological and genetic problems remain completely unaddressed by a gram of electronics on a 4-meter sail. Starshot is a real achievement on its own terms, and its own terms are profoundly limited. Of all the interstellar concepts that actually exist in funded, active engineering, this one is the closest to feasible, and even it may not work until the second half of this century, if then. The contrast between what it can do and what humanity actually needs points toward a concept that captured imaginations for decades before being exposed as fundamentally flawed. It was beautiful while it lasted. Robert Bussard was a physicist, and in 1960 he published a paper proposing the most elegant solution to the rocket equation's tyranny that anyone had ever conceived. The core insight was this: the interstellar medium, the space between stars, is thin but not empty. Roughly one hydrogen atom exists per cubic centimeter throughout the galaxy. Carry enough empty space with you, and you carry a fuel supply as large as the cosmos itself. Bussard proposed equipping a starship with an enormous electromagnetic field shaped like a funnel, scooping interstellar hydrogen from a head, fusing it in a reactor, and expelling the products as thrust. The faster the ship moved, the more hydrogen it scooped, meaning acceleration could in principle be sustained indefinitely with no fuel carried from Earth. The concept launched directly into the scientific imagination and stayed there for decades. Larry Niven used it as the technological backbone of an entire science fiction universe spanning multiple novels. It appeared in textbooks as a plausible near-future technology. Astronomers discussed it at conferences. For roughly 15 years, the Bussard Ramjet was treated as an engineering challenge, awaiting solution rather than a physical problem awaiting examination. The examination, when it came, was thorough and unforgiving. The first fatal problem involves the fusion reaction itself. Bussard assumed the scooped hydrogen could be fused by a ship-sized reactor. The fusion process that actually occurs in stars, the proton-proton chain, requires conditions found only at stellar cores. Pressures and temperatures so extreme they can only be sustained by the gravitational weight of a star pressing inward from all directions. In the Sun's core, the average proton waits approximately 9 billion years before successfully fusing with another proton. That extraordinarily slow reaction rate is sustained by the enormous number of protons involved. A ship-sized reactor cannot replicate stellar core conditions. There is no compact engineering approach that makes proton-proton fusion happen at useful rates. The second problem is drag. A magnetic scoop collecting interstellar hydrogen does not just scoop the hydrogen, it interacts with it. The hydrogen and charged particles in the interstellar medium push back against the field. In 1974, physicist John Ford Fishback worked out the mathematics rigorously. The structural components of the magnetic coils impose an upper limit on how hard the field can be maintained against the ram pressure of collected material. Even using the strongest materials theoretically conceivable, the drag from this interaction ultimately exceeds the thrust at any realistic fusion efficiency. The ship decelerates. A 2021 paper in Acta Astronautica by Peter Schatzschneider and Albert Jackson confirmed what the preceding decades of analysis had suggested. The original Bussard Ramjet design is physically non-viable. The drag exceeds the thrust. Modified versions, concepts where a ship carries some fuel from the start and attempts to supplement it with scooped hydrogen, face the same fusion-ignition problem. The scoop size required to gather enough material for useful thrust, given the low density of interstellar space, would need a radius of roughly 2,000 kilometers. Maintaining a magnetic funnel that large while traveling at relativistic velocity is not a solvable engineering problem. It is a physics problem with an unfavorable answer. None of this diminishes the elegance of the original idea. The instinct that pointed toward free fuel in the void was the right instinct, the kind of thinking that genuine breakthroughs come from. The universe's hydrogen is real, the energy locked in fusion is real, and the impulse to use both is entirely rational. The problem is that the universe does not cooperate with the specific mechanism required. The interstellar medium turns out to be an obstacle as much as a resource, and the physics of stellar fusion refuses to scale downward into a machine you can fit on a ship. Every concept explored so far has hit the same pattern. Extraordinary theoretical performance meets a physical or engineering barrier that deflates it. Chemical rockets hit the combustion ceiling. Ion drives hit the thrust floor. Solar sails hit the distance drop-off and the braking problem. Nuclear thermal hit cancellation. Orion hit a treaty. Fusion waits for engineering that does not exist. Antimatter waits for a production miracle. Laser sails work for grams. The Ramjet does not work at all. Each barrier has a different texture, but they all point toward the same underlying truth. Moving mass across cosmic distances is extraordinarily hard, and the human body is an extraordinarily expensive piece of cargo. To understand why the physics remains generous even when the engineering fails, you have to go back to 1905, to a young patent clerk in Bern, Switzerland, who discovered something about time that changed everything. Albert Einstein published his special theory of relativity in 1905, and buried inside it was a consequence so strange that physicists argued about its meaning for decades, before experiments settled the question permanently. Moving clocks run slow. A clock that is in motion relative to an observer ticks at a slower rate than a clock that is stationary relative to that observer. This is not a statement about the clock's mechanisms, about springs or pendulums or batteries wearing out. It is a statement about time itself. The rate at which time passes depends on how fast you are moving. The mathematical relationship is elegant. The ratio of the moving clock's tick rate to the stationary clock's tick rate depends only on velocity, specifically on how close that velocity is to the speed of light. At ordinary speeds, the difference is negligible. At 90% of light speed, a moving clock ticks at roughly 44% of the rate of a stationary one. At 99% of light speed, it ticks at about 14%. At 99.9%, the ratio drops to about 4.5%. Time dilation is not gradual and linear. It accelerates as velocity approaches the cosmic speed limit, governed by the same equations at every velocity. The first serious experimental test of this prediction came in October 1971. Physicists J.C. Huffele and Richard Keating flew 4 cesium beam atomic clocks around the world on commercial jet flights, once traveling eastward and once traveling westward. Commercial jets travel at roughly 800 kilometers per hour, an almost negligible fraction of light speed. The predicted time differences were measured in nanoseconds. And yet the atomic clocks, precise enough to measure such tiny differences, came back from their flights ticking at exactly the rates special and general relativity predicted, differing from identical clocks that had remained on the ground by 69 nanoseconds on the eastward flight, and gaining 273 nanoseconds on the westward flight, exactly as calculated. The experiment that most people interact with every day provides even more direct proof. The global positioning system works by measuring the time it takes for signals to travel from satellites to receivers on the ground. The satellites move fast enough and are far enough from Earth's gravitational field that relativistic effects cause their onboard clocks to run at rates slightly different from surface clocks. Engineers accounted for this precisely, programming daily corrections into the system. Without those corrections, accumulated relativistic errors would cause navigation accuracy to drift by approximately 11 kilometers every single day. Every time a phone gives you a turn-by-turn direction, time dilation is being actively corrected for in the background. It is not a theoretical prediction. It is engineering infrastructure. This established fact, proven on airplanes and baked into satellite technology, is what makes the 45-year claim in this documentary's opening physically real rather than speculative. The same equations that tell the global positioning system engineers how to correct their satellite clocks. The same equations confirmed by 4 atomic clocks on commercial flights in 1971 also predict what happens to a traveler's clock as their velocity approaches the speed of light. The dilation grows, time slows further. At velocities close enough to light speed, the traveler's experienced time compresses dramatically against the time ticking away on Earth. But experimental verification of time dilation at small velocities does not automatically answer the question of what happens when two observers in relative motion eventually meet again. The physics there leads to what sounds like a contradiction, one that worried physicists for years before the resolution was found. The resolution has no loopholes, and it has everything to do with what actually happens to the human body of a relativistic traveler who turns around and comes home. Suppose one of 2 identical twins boards a spacecraft and accelerates to 90% of the speed of light, travels to a star 4 light years away, decelerates, turns around, accelerates back, and comes home. The traveling twin has aged less. The Earth twin has aged more. That is the prediction. From the traveling twin's perspective, though, wasn't it the Earth twin who was moving? Shouldn't the situation be perfectly symmetric, with each twin having aged less from the other's perspective? The apparent paradox dissolves when you account for what the traveling twin actually does. The traveling twin changes direction. Changing direction means decelerating and re-accelerating, which means experiencing forces. The Earth twin feels no such forces. Special relativity's symmetry applies only to observers in constant, unaccelerated motion relative to each other. The moment one observer accelerates, the situation becomes asymmetric, and the predictions diverge. The traveling twin's clock genuinely runs slow. The Earth twin's genuinely does not. When they reunite, the difference is real and measurable in biology. At 90% of light speed, the Lorentz factor, the ratio of Earth's elapsed time to the traveler's elapsed time, is approximately 2.3. A 10-year journey in the traveler's experience corresponds to about 23 years on Earth. The traveling twin returns biologically 10 years older to an Earth twin who is 23 years older. The difference is not an illusion. The traveling twin has literally had fewer heartbeats, fewer cell divisions, fewer years of wear on every organ and tissue. The biological aging is real. At higher speeds, the effect becomes far more extreme. At 99% of light speed, the Lorentz factor climbs to about 7. A traveler's 10-year journey corresponds to roughly 70 years on Earth. At 99.9%, the factor reaches about 22. At 99.99%, it passes 70. Each additional 9 in the decimal pushes the Earth-side clock faster and faster, while the traveler's clock slows further and further relative to it. This is not a mechanical trick or a limitation of any specific kind of clock. Atomic clocks, quartz oscillators, biological processes, radioactive decay, every physical process that constitutes time runs slow for the moving observer. The traveler does not just experience time differently than a stationary observer. They move through less of it in an absolute physical sense. Fewer atoms decay, fewer cells divide. The human body aboard a relativistic spacecraft experiences a genuine physical reduction in the total amount of time it consumes on a journey. The practical question is, what speeds make this useful? At 50% of light speed, the dilation factor is about 1.2, meaning the traveler experiences about 15% less time than Earth. Real, but mild. At 90%, the factor is 2.3. At 95%, it reaches about 3.2. These are meaningful compressions, but still do not transform multi-decade journeys into something a single human lifetime can absorb comfortably. To get to the factors of 10, 20, or 100 that make truly long journeys survivable, the velocity must push above 99% of light speed and beyond. The mathematics says this is allowed. The equations do not forbid velocities of 99.9 or 99.99% of light speed in principle. They simply describe what happens. What they also describe, and what the next chapter addresses in full, is what a ship must actually do to sustain an acceleration toward those speeds, and why a traveler would hardly notice the journey compressing around them. Imagine a ship that accelerates constantly at 1 gravity, 9.8 meters per second squared, the pull you feel toward the floor right now, sustained indefinitely in the direction of travel. The crew feels normal weight at all times. They walk around the ship. They sleep in real beds with real pressure against the mattress. Their bones maintain density because gravity is doing exactly what it does on Earth. There is no floating, no muscle atrophy from weightlessness, no disorientation from living in a bubble of simulated gravity generated by rotation. The acceleration itself is the gravity, and it is perfectly natural from the crew's perspective. From the perspective of an external observer watching the ship, something increasingly strange is happening. The ship is accelerating, which means it is getting faster, but it cannot exceed the speed of light because that is a hard physical law with no exceptions and no loopholes. As the ship approaches light speed, it requires exponentially more energy for each additional increment of velocity. The energy available does not change. The rate of actual speed gain slows. From outside, the ship's velocity climbs toward the cosmic speed limit, like a graph approaching an asymptote, always getting closer, never reaching it. From inside the ship, none of this is perceptible. The crew feels the same steady gravity they have always felt. But the universe they are moving through is being physically compressed in the direction of travel. The relativistic effect that squeezes time also squeezes perceived distance for the traveler. A journey that covers billions of light-years of physical space from Earth's reference frame can take a much shorter time from the traveler's reference frame, because from inside the ship, those billions of light-years have been relativistically compressed into something the ship can traverse in a human lifetime. The relativistic rocket equations describing this scenario were fully worked out from Einstein's original framework and are well established. They describe a ship under constant acceleration in terms of proper time, the time on the traveler's clock, and coordinate time, the time on Earth's clock. A ship accelerating at 1 gravity toward Proxima Centauri, 4.24 light-years away, with the midpoint flip where deceleration begins, delivers its passengers in about 3.53 years of their experienced time. Earth elapsed time for the same journey, 5.85 years. Close enough that the difference is significant, but not catastrophic. Push the destination farther, and the numbers become increasingly dramatic, because the ship spends more time at genuinely relativistic velocities where the Lorentz factor is large. The traveler's clock keeps ticking at its steady rate. Earth's clock, from the traveler's perspective, starts to race. For nearby stellar destinations, the dilation is modest. For anything significantly farther, the ship must reach velocities where the Lorentz factor is not 2 or 3, but 20 or 200 or 2 million. At those speeds, a year of the traveler's life corresponds to decades or millennia on Earth. This is the framework that makes the 45-year claim real rather than speculative. A constant one-gravity ship is not a fictional device. It is a thought experiment built on established physics, describing what would happen if such a ship could be fueled and sustained. The equations that govern it are the same equations correcting your phone's the global positioning system right now. The numbers they produce for various destinations are not estimates or approximations. They are precise consequences of well-tested physics. Those numbers, laid out in full, are some of the strangest things the sciences have ever produced. They need to be encountered slowly, one at a time, because the cumulative effect of reading them in sequence is a kind of vertigo that takes a moment to recover from. A constant one-gravity ship departing Earth toward Proxima Centauri, the nearest stellar system, arrives after 3.53 years of the traveler's experienced time. Earth has aged 5.85 years during the same journey. The difference is real but modest. A traveler leaving at age 30 arrives biologically aged 33 and a half, stepping out onto a world at a star that has been shining for 5.85 more years than when they left. In cosmic terms, this is barely a rounding error in the biography of the universe. Keep pushing the destination farther, and the numbers change character entirely. The Pleiades star cluster, which you can see with the naked eye on a clear winter night, sits about 444 light-years from Earth. A one-gravity ship reaches it in under 12 years of the traveler's time. Earth has aged 446 years during that same journey. The traveler steps out biologically in their early 40s. Every human alive at departure is dead. Their great-grandchildren's great-grandchildren are living their own lives on an Earth that has moved through 4.5 centuries of history since the launch. The galactic center, roughly 26,000 light-years away, is the hub around which our entire stellar neighborhood orbits. A one-gravity ship reaches it in under 20 years of the traveler's time. Earth has aged approximately 27,000 years. When the Pleiades traveler left, the Renaissance was 4 centuries past. When the Galactic Center traveler left, the last ice age had barely ended. The Andromeda Galaxy, the nearest major galaxy to our own, sits about 2.5 million light-years away. A one-gravity ship reaches it in under 29 years of the traveler's time. Earth ages 2.5 million years. The traveler departs a civilization using smartphones and returns, biologically in their late 50s, to a world where our species has had 2.5 million years to evolve, diverge, flourish, or disappear. And the edge of the observable universe, every galaxy, every photon that has ever reached a human telescope, the entire 13.8 billion light-year span of everything we can see from here, roughly 45 years of the traveler's time. The traveler leaves Earth at 30 and arrives at the boundary of the knowable cosmos before turning 75, while Earth ages by a span equal to the current age of the universe. These numbers are precisely calculated from the relativistic rocket equations. They are as well established as any prediction in physics. They are also almost completely irrelevant to any mission any civilization remotely resembling ours could consider, because of a single number that the same equations also produce: the fuel required. The relativistic extension of the Tsiolkovsky equation, applied to a one-gravity ship with a perfect engine whose exhaust reaches light speed, calculates the fuel mass needed for each journey. A round trip to Proxima Centauri requires a fuel-to-payload mass ratio of roughly 38:1. A round trip to the galactic center requires a ratio that exceeds the total mass of all the planets in the solar system combined. A round trip to Andromeda requires more fuel than exists in the Sunday. A trip to the edge of the observable universe requires more mass than the observable universe itself contains. The 45-year claim is physically real. Every number in the table is a precise consequence of verified physics, and every single one of those journeys is made impossible by the mass of propellant required to sustain the acceleration needed to produce the time dilation that makes them survivable. What physics gives with the Lorentz factor, physics takes away with the fuel equation. This gap deserves to be understood precisely because it is the central fact of the entire documentary. It is not a gap in knowledge, it is a gap in energy. The Tsiolkovsky rocket equation, the one derived in that log cabin in 1897, has a relativistic extension. When a ship approaches the speed of light, the ordinary version of the equation no longer gives accurate answers, because the physics of motion at those velocities obeys Einstein rather than Newton. The relativistic version is more complicated mathematically, but it asks the same underlying question. For a given exhaust velocity and a given change in velocity, how much fuel does the ship need relative to its final payload mass? At low speeds, the two versions of the equation agree. Near the speed of light, they diverge, and the relativistic version is the unforgiving one. Apply it to the destinations in the previous chapter, using the most generous possible assumptions. Assume a perfect antimatter engine whose exhaust reaches the speed of light, the theoretical maximum exhaust velocity for any propulsion system based on known physics. Assume a round trip to each destination, meaning the ship must accelerate to cruise speed, decelerate to arrival, accelerate back toward home, and decelerate to rest. Each phase burns fuel, and the fuel from the later phases must be carried through all the earlier ones, which multiplies the total requirement. For a round trip to Proxima Centauri at constant one-gravity acceleration, the fuel-to-payload mass ratio comes out at roughly 38:1. For every kilogram of ship, crew, equipment, and supplies, the ship must carry approximately 38 kilograms of fuel. This is demanding by any measure, roughly comparable to the fuel ratio of a large chemical rocket, but it is at least a number a civilization could in principle aspire to. A ship massing 1,000 tons all up would need around 38,000 tons of perfect antimatter propellant. Given that all of humanity has ever produced less than 20 nanograms of antimatter, this remains fantastical, but the ratio itself is not absurd. Push the destination to the Pleiades cluster, about 444 light-years away, and the fuel ratio grows past anything a ship could carry. The required mass of propellant exceeds the total mass of all the planets in the solar system combined. The ship's fuel tank would need to be larger than a planet, fueled by a substance that does not exist in macroscopic quantities. For the galactic center, 26,000 light-years away, the ratio grows by further orders of magnitude. The required propellant mass exceeds the mass of all the stars in a large galaxy. There is no engineering solution that approaches this constraint. There is no material that could be mined, no energy source that could be tapped, that would come within many orders of magnitude of the required amount. For Andromeda, 2.5 million light-years away, the numbers pass beyond the mass of the observable universe's visible matter. The fuel required to make a round trip to the Andromeda galaxy in 45 years of your experience time is more matter than exists in everything humanity has ever detected with any telescope combined. For the edge of the observable universe, the equation produces a fuel mass so large it has no meaningful physical counterpart. The number exceeds the total mass-energy content of the entire cosmos by factors that cannot be expressed in terms of any real physical object. It is a number that can be written but corresponds to nothing that exists. This is the full shape of the gap. Physics grants time dilation freely. The relativistic equations impose no barrier. Every destination in the table is reachable in a human lifetime by the math of motion. Every single destination is made physically unreachable by the math of fuel. The same equations that enable the 45-year claim also close the door on it with the fuel requirement. The most advanced propulsion concept available, a perfect antimatter rocket producing no detectable amount of propellant, cannot come close to what even the nearest destinations demand for a round trip. The one-gravity journey to the observable universe's edge is the most eloquent example of a physical fact that is simultaneously completely true and completely inaccessible. Every equation checks out. Every calculation follows correctly from well-established physics. And yet the energy required exceeds the total energy content of the cosmos you are trying to traverse. The most optimistic scenario, something short of full cosmic exploration and aimed at merely reaching the nearest stellar neighbor within a single human lifetime, requires velocities well above what current engineering can dream of. How high those velocities need to be, and what the curve between them and the limit looks like, is where the story sharpens next. At 10% of the speed of light, time dilation reduces the traveler's experience time by about half of 1% compared to Earth time. The journey takes slightly less experience time than coordinate time, but the difference is so small it would never be noticed in a human lifetime. At 30% of light speed, the compression reaches about 5%. At 50%, about 15%. These are real effects, measurable by sufficiently precise clocks, but they do not transform interstellar travel. A journey that takes 100 years in Earth time still takes roughly 85 years in the traveler's experience time at 50% of light speed. The human lifespan does not survive that trip. The character of time dilation changes fundamentally above 90% of light speed. The Lorentz factor, the number by which Earth's elapsed time exceeds the traveler's, passes 2 at 90% and begins accelerating rapidly. At 95%, it reaches about 3.2. At 99%, it passes 7. At 99.9%, it climbs above 22. At 99.99%, it exceeds 70. Each additional 9 added to the decimal takes the factor higher, but the energy cost of each additional 9 grows without limit. The relationship between speed and Lorentz factor is a curve with a specific mathematical shape. It rises slowly at low velocities, curves upward at moderate fractions of light speed, and then bends almost vertically as velocity approaches the cosmic limit. The dramatic time compression that makes galaxy crossing survivable lives in that nearly vertical section of the curve, where velocity is so close to light speed that the difference between the two numbers is measured in fractions of a percent, but the ratio of Earth time to traveler time is measured in thousands or millions. Getting to that section of the curve requires enormous energy. Staying there requires maintaining that enormous energy output continuously. Every propulsion concept examined so far runs out of practical reach long before reaching the modest velocities where time dilation becomes even slightly useful for compressing interstellar journeys. Voyager 1 and Parker Solar Probe operate at fractions of 1% of light speed, where dilation is essentially unmeasurable. Breakthrough Starshot aims for 20%, where dilation saves a few months on a 20-year journey. Orion nuclear pulse propulsion might reach 10%. At the same mild end of the dilation curve, the velocities that actually compress years to decades, decades to years, are 10 times higher than any proposed near-future human technology can approach. This is what makes the asymptote problem the central engineering challenge of interstellar travel. The physics does not forbid any of those higher velocities. The equations describe them without complaint. The fuel required to reach them escalates in a way that mirrors the Lorentz factors curve in reverse. Each additional percent of light speed costs exponentially more until the fuel requirements exceed any plausible supply. The honest answer, when you strip away both the despair and the enthusiasm, is that meaningful time dilation. The kind that turns a multi-decade journey into a multi-year one requires velocities humans cannot currently approach or plausibly approach within this century. It is theoretically available to a civilization with access to energy sources several orders of magnitude beyond our own. For our civilization, the physics is generous, and the engineering is nowhere near. 2 further walls remain, even if propulsion were somehow solved. One of them is invisible. The other dismantles the body from the inside. The Earth's magnetic field is a structure generated by the churning of molten iron in the planet's outer core, extending tens of thousands of kilometers into space in every direction. Together with the dense atmosphere below it, this field intercepts the vast majority of the high-energy particle radiation arriving from deep space before any of it reaches a living cell at the surface. Standing outside on a clear afternoon, you are being bombarded by a universe's worth of radiation, and almost none of it reaches you because thousands of kilometers of air and a planetary magnetic field are absorbing the assault on your behalf. You have never lived a day without this protection. Step outside that protection, and the radiation environment changes in ways that are difficult to convey with numbers alone. Astronauts living in low Earth orbit, still inside the protective reach of the magnetosphere, but above most of the atmosphere, receive radiation doses roughly 100 times higher than people on Earth's surface. On a transit to Mars, outside the magnetosphere entirely but still within some shielding influence of the solar wind, a crew would accumulate radiation doses approaching or exceeding the career limits set by space agencies for some crew members before even landing on Mars. A Mars transit takes between 6 and 9 months each way. The radiation comes from 2 separate sources, each with its own character and its own dangers. Galactic cosmic rays are high-energy protons and atomic nuclei ejected from distant supernovae at speeds approaching light speed. They arrive from every direction continuously, and they carry enough energy to pass through almost any reasonable amount of shielding. Heavy shielding absorbs some of the primary particles but creates secondary radiation as the particles interact with shield material, partially defeating the purpose and adding mass that must be accelerated. No passive shielding strategy has solved this problem without the mass penalty becoming prohibitive. Solar particle events are sudden storms of energetic protons released by solar flares or coronal mass ejections. They can arrive with little warning and deliver dangerous doses within hours if no shelter is available. On a Mars mission, the crew can shelter in the most shielded portion of the spacecraft. On an interstellar mission lasting decades, solar events from the home star become irrelevant, but galactic cosmic rays become the permanent background condition for every hour of every year of every decade of the voyage. The biological effects of decades of unshielded cosmic ray exposure are not pleasant projections. Central nervous system damage, increased cancer risk, accelerated cataract formation, and possible acceleration of other aging processes are all implicated in animal studies at high radiation doses. An interstellar crew living in the cosmic ray field for 20, 30, or 40 years would be accumulating damage throughout their voyage. The dose might not be immediately lethal, but the cumulative effect on cognitive function, cancer probability, and lifespan could be severe. Active magnetic shielding, a powered field surrounding the ship that deflects charged particles the way Earth's magnetosphere does, is theoretically possible but requires enormous electrical power sustained over the entire voyage duration. The power source, capable of running such a system for decades, also doesn't exist in any near-future technology. The radiation problem has no cheap engineering solution, and any expensive one loops back to the same mass and energy budget that defeated every propulsion concept already examined. Radiation is the first wall that the body meets outside Earth's protection. The second wall needs no external source at all. It grows from the inside, from the simple fact that the human body was built for one specific gravitational environment and deteriorates measurably when removed from it. On the 84th day of the third Skylab crew's mission in 1973, physicians analyzing bone density data from the crew found that heel bone density had dropped by approximately 8% from pre-flight baselines. 3 months in space, and bones were already showing deterioration equivalent to the early stages of the disease that shrinks elderly patients' skeletons. By 140 days, the loss approached 19%, equivalent to clinical osteoporosis, compressed into a single mission for otherwise healthy people in the prime of their lives. Bone loss in microgravity follows a straightforward mechanical logic. Bone is not static tissue. It rebuilds itself continuously, with specialized cells breaking down old material and others depositing new. The process is regulated partly by the mechanical loads bone experiences. Weight-bearing activity sends signals that tell the skeleton to maintain its density. Remove gravity, remove weight-bearing, and those maintenance signals disappear. The breakdown process continues. The rebuilding process slows. Over weeks and months and years, the skeleton thins. Muscle follows a similar logic with a faster timeline. Measurable muscle mass loss begins within days of entering weightlessness. Without the constant work of holding upright posture and moving against gravity, large muscle groups begin to atrophy rapidly. Current exercise countermeasures on the International Space Station, which include daily resistance training using specialized equipment, reduce the rate of loss significantly, but do not stop it entirely. Crew members returning from 6-month missions need physical rehabilitation to walk normally. They did not simply experience discomfort. Their bodies had structurally changed. A one-way interstellar mission of 20 years under current understanding of human physiology, without artificial gravity or biological countermeasures beyond what exists today, would deliver its crew in a physiological state, difficult to predict with confidence and easy to envision with alarm. Bone density reduced by amounts that make fracture risk from ordinary activity severe. Muscle mass diminished to a degree that basic physical function is compromised. Cardiovascular fitness altered by the different demands of a body that has not spent years working against gravity. All of this before accounting for the radiation damage accumulating simultaneously. Artificial gravity solves most of the bone and muscle problem by simulating the gravitational loads the body evolved to work against. A rotating section of the ship, spinning fast enough to produce centripetal acceleration, equivalent to 1 gravity, gives the crew an environment the skeleton and muscle systems recognize as normal. The physiological benefits are real. The engineering costs are significant but manageable at scales needed for a generation ship. The added mass, the structural complexity, and the mechanical challenges of a rotating habitat are serious engineering problems rather than physical impossibilities. What cannot be engineered away is the isolation. Even if a ship solved gravity, solved radiation, solved propulsion, solved fuel, the crew inside it would still be sealed in a metal environment with no possibility of leaving, no real-time connection to Earth, no horizon beyond the ship's walls, for years or decades. The Skylab and International Space Station data describe bodies under physical stress. The data from simulated long-duration missions describe something harder to quantify and harder to fix. Minds under psychological stress of a kind that has no precedent in human experience. That wall is the next one to examine, and it may be the most honest description of what interstellar travel would actually feel like from the inside. In February 2010, 6 men entered a series of interlocked modules in Moscow and did not come out for 520 days. The isolation study, called Mars 500, was not a space mission. It was a simulation on the ground, within a city, surrounded by millions of people who could have opened the hatch from outside at any moment. The participants knew this, and still, by the end, the psychological toll was measurable, documented, and sobering. Researchers monitoring the crew throughout the study found that activity levels fell steadily as the mission progressed. Sleep schedules drifted, disrupted entirely by the removal of every cue that normally anchors the human body to a time of day. Natural light, temperature shifts across the afternoon, the ambient sounds of an outdoor environment, the small social rhythms of moving through a shared world, all of it stripped away. 2 of the 6 crew members showed behavioral markers that, in a clinical context, would be associated with elevated risk factors for depression. They were healthy volunteers, rigorously screened for psychological resilience, fully aware of the study's purpose. The environment changed them anyway. Communication throughout much of the study was artificially delayed to simulate the signal travel time between Earth and Mars. Even at delays of 20 minutes or less, researchers documented measurable reductions in crew morale and their reported sense of connection to the support teams outside. The delay converted every exchange into a series of unsynchronized messages, each one arriving after the emotional moment that prompted it had already passed. Receiving comfort 20 minutes too late, or information 20 minutes stale, turned communication into something that reminded the crew of connection while failing to provide it. Mars 500 lasted less than 18 months. A real Mars transit with current propulsion takes between 6 and 9 months each way, plus surface operations. Crew members on such a mission would be away from Earth for somewhere between 1.5 and 2.5 years. The simulation ran near the upper end of that range, and what it found was already concerning. For an interstellar mission, the duration shifts by a factor that makes the entire study look like a long weekend. At 20% of the speed of light, the nearest star system is a 20-year journey. A message sent home the day of arrival would take 4 years to reach Earth. A reply would arrive 4 years after that. 8 years between asking a question and receiving an answer. For destinations farther than the nearest stars, that delay grows proportionally, and at some point stops being a communication inconvenience and becomes a defining feature of existence aboard the ship. No response will come in any traveler's lifetime. The people inside the hull would understand, with a clarity no previous generation of explorers has ever had to confront, that they are beyond recovery. Every earlier era of exploration had a returning point, a harbor waiting, a civilization that would one day receive them back. An interstellar crew has none of that. Every decision, every emergency, every loss, every question about meaning would belong entirely to them and to whoever shares the sealed metal world around them. There is a reason researchers have studied whether it would be better to simply not be conscious for most of the trip. Whether the body agrees with that proposal is where the story leads next. The idea of sleeping through the hard parts has a practical basis in real medicine. Therapeutic hypothermia, the controlled cooling of a patient's core body temperature to around 92 degrees Fahrenheit, is already a standard emergency intervention after cardiac arrest and certain trauma injuries. At that reduced temperature, metabolic rate drops by 50 to 70%. The brain and heart and organs slow down, buying time for physicians to work. Patients cooled to this state for hours and return to normal temperature afterward recover well. The technique is not experimental, it is routine. Spaceworks, enterprises, working under research grants from the Space Agency's Innovative Advanced Concepts program across multiple phases starting around 2013, proposed extending this same principle to cover interplanetary transits. Their concept would cycle crew members through 2-week periods of induced torpor across a journey of months, with small teams rotating in and out of consciousness to maintain minimal ship operations. The metabolic savings alone would reduce food, water, oxygen, and waste requirements dramatically, simplifying the life support burden and cutting mass. The most compelling supporting data came from an unexpected direction. Hibernating animals do not experience the bone density loss that plagues human spaceflight. Arctic ground squirrels spend 6 to 8 months in hibernation each year, during which they are essentially motionless and emerge in spring with their skeletal architecture essentially intact. Bears show the same pattern. The cellular mechanisms of hibernation appear to suppress the bone remodeling imbalance that microgravity triggers in humans. Something about metabolic suppression preserves the skeleton in ways that exercise routines in weightlessness cannot fully replicate. The Spaceworks studies also identified benefits for muscle preservation, radiation exposure reduction through simply slowing the body's metabolic processes, and the psychological relief of not being consciously present for long stretches of isolation. A crew member who spends most of a months-long Mars transit in induced torpor is not enduring the psychological accumulation of isolation that the Mars 500 study described. From their subjective experience, most of the journey does not happen. The honest summary of where this technology stands is that it works briefly in injured patients under carefully controlled hospital conditions. Healthy human torpor lasting weeks or months has not been tested. The brain effects of extended sedation at those timescales are not yet characterized. The bone and muscle preservation seen in hibernating animals is real and genuinely exciting. But animals that evolve to hibernate have metabolic machinery honed over millions of years of selection. Humans did not. Whether human physiology would respond the same way to induced cooling, or whether the differences in biochemistry would produce different outcomes, is a question that requires substantially more animal and human research before any reasonable answer is available. The European Space Agency regards metabolic suppression as a promising concept requiring further research before any mission application. The American Space Agency has taken a similar position. The idea is serious enough to fund and study. It is not ready to stake lives on, and even if it were perfected for a Mars transit, the question of whether it scales to years or decades of travel remains entirely open. A ship sleeping through a 20-year interstellar journey faces a different class of problem from a ship sleeping through a 6-month Mars transit, and the problem that does not yield to sleep at all is written into the passengers' cells before they ever board. In the 1990s, anthropologist John Moore at the University of Florida ran calculations on the minimum population needed to sustain a multi-generational interstellar voyage, and arrived at a number that became widely cited: 150 people. A crew of 150 could, in his analysis, maintain enough genetic diversity and social structure to survive a 2,000-year trip to the nearest stars. The number entered planning discussions, appeared in popular writing about generation ships, and became a reference point for anyone thinking seriously about interstellar colonization. Cameron Smith at Portland State University ran his own simulations, working with population modeling software alongside William Gardner O'Kearney, and found that Moore's estimate was dangerously wrong. Smith's simulations tracked genetic diversity across generations under various starting conditions, modeling realistic birth rates, death rates, and disease outbreak scenarios. A population of 150 people, in his models, loses roughly 80% of its genetic diversity within 30 generations. What remains is a genetically impoverished community whose descendants carry the accumulated burden of inbreeding, with recessive genetic diseases surfacing in children that a larger, more diverse founder population would have suppressed. This is not a metaphor or a projection. It is a measurable process, well understood in conservation biology from decades of studying isolated animal populations, and it is not reversible once it advances far enough. A population of 500 fared better but was still insufficient across the timescales. A voyage to any destination beyond the nearest stars would require. Smith's simulations identified 10,000 people as the practical minimum for maintaining genetic health across a long voyage, providing enough diversity to absorb demographic setbacks like a severe disease outbreak, a catastrophic accident, or a period of social fragmentation that reduces reproduction rates. At 10,000, the population can weather those events and emerge on the other side with enough genetic variation intact to establish a viable new civilization. 40,000 people provides a meaningfully safer margin, preserving the full range of the original genetic variation and offering resilience against compounding setbacks. The difference between those two numbers is not arbitrary. It reflects the fact that a disease outbreak killing a third of a 10,000-person population leaves a community that can barely recover. The same event hitting 40,000 people leaves a damaged but viable gene pool. Smith described the goal plainly. With 10,000, a founding population could depart with a genuine cross-section of human genetic diversity, survive even a severe disease outbreak, and arrive in numbers sufficient to form what he called a viable foundation for humanity's next chapter. The implications for any ship design are not incremental. A crew of 10,000 is not a spaceship with a lot of bunks. It is a small city. It requires agriculture, medicine, education, governance, manufacturing, and every other system that a functioning human community requires to sustain itself, all in closed loop, all without resupply or backup, for a voyage that might last centuries. Every kilogram of that city must be accelerated, and every extra kilogram multiplies the already catastrophic fuel requirements from the propulsion chapters. The genetic flaw is the biological constraint. What lives above it is a different kind of problem entirely, the one that does not appear in any engineering specifications or population simulations, the one that has broken more closed human systems than any other force in history. Knowing how many people a generation ship must carry to survive genetically does not solve the deeper question of how those people sustain a crust civilization. A civilization that must remain functional for hundreds of years in a sealed environment, without contact, governed by rules written before departure by people who could not anticipate what centuries of isolation would produce. A 2018 study published in the Journal of the British Interplanetary Society ran population, social stability simulations for multi-generational voyages under different governance models. The results were not encouraging. Even starting with populations close to the minimum size recommended by Smith's genetic models, the simulated communities failed to survive the full duration of a 6,300-year voyage to Proxima Centauri when operating under fixed social rules. The mechanism of failure was consistent. Rigid governance systems that worked well at the start of the voyage became increasingly mismatched to the conditions of the community as generations passed. Small crises that an adaptive society would absorb became destabilizing events in a society locked into behavioral norms set by ancestors the living crew had never met. Adaptive rule systems improved the survival rates in the simulations dramatically, but they could not guarantee mission completion. The problem is that designing a governance system flexible enough to adapt to unpredictable change, while also stable enough to preserve the core technical knowledge and social cohesion required for a multi-century voyage, is a problem that has never been solved by any human civilization in history. Every functioning society on Earth has had access to the outside world as a corrective force. Trade partners, incoming populations, external pressure that shaped internal culture. A generation ship has none of that. The specific knowledge preservation problem is acute. The ship's reactor must be maintained by people, trained by people, trained by people whose teachers may have been born on Earth. The life support system's chemistry must be understood well enough to diagnose and repair failures by engineers several generations removed from any formal training institution. Navigation, communication, medical care, metallurgy, the entire technical basis of keeping a ship operational for centuries must be transmitted as living knowledge, embedded in people who can use it, far beyond what written records alone could preserve. The maritime history of isolated islands offers cautionary data. Specialized technical knowledge is lost in isolation faster than any archive can compensate for. The people born on the ship did not choose the mission. They will live their entire lives inside it. Some will spend a lifetime maintaining systems they did not build for a destination they will never see, in service of goals established by ancestors they know only as names in records. Designing a civilization where that arrangement produces motivated, capable, psychologically healthy people across 10 or 20 or 50 generations is not an engineering problem. It is the hardest problem in social science, and social science has never had to solve it under these conditions. The generation ship is not just a vessel. It is a political system, an educational institution, a healthcare network, a cultural tradition, and a genetic lineage, all sealed in the same metal hull, all required to function simultaneously without external input for as long as the journey takes. Strip away the romanticism of it, and what remains is a sobering question. Has humanity ever built anything that worked perfectly for centuries? And when it answers that question honestly, it is ready to take stock of what each technology tier actually offers within the next 100 years. Step back from the thought experiments and the extreme scenarios and look at the realistic technology tiers available within this century, stripped of optimism. The honest hierarchy runs from achievable to theoretical, and the gap between the top and the bottom of that list is one of the largest in engineering history. Chemical rockets can get humans to Mars and back. The journey takes 6 to 9 months each way. With current propulsion, the radiation exposure approaches career limits for some crew members, and the physiological demands of long-duration weightlessness require serious countermeasures and post-mission rehabilitation. None of that is insurmountable. It is hard, expensive, and risky, and it is achievable with technology that already exists. It is the one tier in this hierarchy with no physics barriers remaining. Nuclear thermal propulsion, if political will ever matches the physics, could cut a Mars transit roughly in half, reducing radiation exposure and physiological degradation proportionally. The nuclear thermal test program proved the technology in 1972. Its successor program was cancelled in 2025 for budget and institutional reasons. Not because the concept failed. Congress pushed back on the cancellation, with the Senate directing a minimum of $110 million toward nuclear propulsion in its 2026 budget markup. And the debate continues. With nuclear thermal, human reach extends toward the asteroid belt and the inner moons of Jupiter on timescales of years rather than decades. It is within reach. It requires someone to decide to build it and to keep that decision intact long enough to finish. Ion drives and solar sails move robots across the solar system with patience and efficiency that no crewed mission requires, but robotic missions exploit well. Neither technology moves humans meaningfully faster than chemical rockets on human-relevant timescales. Nuclear pulse propulsion, the Orion concept, could theoretically push a large ship to between 3 and 10% of light speed. That range covers the enormous distance between current technology and interstellar capability. The physics have never been seriously doubted. The partial test ban treaty of 1963, the institutional inertia of 60 years without serious development, and the public acceptance problem for a ship that operates by detonating nuclear weapons remain barriers with no current path around them. The treaty did not resolve the physics. It resolved the politics in the wrong direction. That distinction matters. A physics barrier means the technology cannot be built. It requires discovering new science. An institutional barrier means the technology could be built but has not been because the political and legal environment does not allow it. Every other item in this hierarchy is blocked by physics or engineering. Nuclear pulse propulsion is blocked by a treaty and a series of budget decisions. That is a fundamentally different kind of obstacle, and one that a different political environment could theoretically dissolve. Everything beyond nuclear pulse, including fusion propulsion, antimatter drives, and laser arrays pushing crewed ships, requires either breakthroughs in areas where no timeline is predictable, or a civilization with energy resources that our current one does not possess and may not reach within the next century. These are not pessimistic conclusions. They are the result of reading the engineering and the physics in the same document without letting one override the other. The line between hard but buildable and requires a revolution runs somewhere around nuclear pulse propulsion. Below that line is a century's worth of achievable work. Above it is everything else. The first step toward the other side of that line is already being designed. In 2021, a team led by the Johns Hopkins Applied Physics Laboratory completed a detailed engineering study commissioned by the Space Agency for a mission unlike any it had formerly studied before. Previous spacecraft had left the solar system accidentally as a byproduct of gravity assists and orbital mechanics optimized for other goals. This proposal was different. It called for a spacecraft designed from the start with a single purpose: intentionally entering interstellar space and studying it. The proposed interstellar probe would reach between 500 and 1,000 times Earth's distance from our star within 50 years of launch, traveling at roughly 15 to 20 times Earth's distance from the star per year. For comparison, Voyager 1, currently the most distant human-made object, has taken nearly 50 years to reach about 163 times Earth's distance. The proposed probe would travel 5 times faster and reach regions no instrument has ever been designed to study. The approach to achieving that velocity combines 2 techniques. First, a close flyby of our star, coming within a few solar radii of the photosphere to pick up the maximum gravitational velocity boost, the same principle that accelerated every planetary probe in history, but executed at unprecedented proximity. Second, a large solar sail deployed at the point of closest approach, where sunlight pressure is at its most intense, giving an additional push that carries the probe outward through the solar system and beyond. The destination is not another star. The mission would not reach Alpha Centauri in any human-relevant time frame. What it would reach, for the first time intentionally, is the interstellar medium itself. The thin gas and dust and magnetic fields that fill the spaces between stellar systems, the environment that any interstellar ship would eventually have to traverse for decades or centuries. Voyager instruments were not designed for this environment and were already degraded by decades of operation when they crossed the heliopause. The interstellar probe would arrive at that boundary with full scientific instrumentation optimized specifically for what lies beyond. As of early 2026, the mission remains unfunded. The study is complete and technically serious. A real launch opportunity exists in principle within the next decade or two, depending on when the optimal planetary alignment for the close solar flyby occurs. The cost would be comparable to a large planetary science mission, not an extravagant departure from what space agencies have spent on other flagship projects. The interstellar probe matters for this story not primarily for what it would find, though what it would find about the interstellar medium could directly inform every future deep space mission design. The dust density, the magnetic field structure, the charged particle environment that any crewed ship or robotic probe would navigate for decades on an interstellar crossing. Every assumption built into that mission planning is currently built on theoretical models rather than direct measurement. It matters because its existence represents a conceptual shift, from treating interstellar space as a theoretical domain defined by the distance to other stars, to treating it as a specific environment that can be studied on a human-relevant schedule using near-future technology. The distance to the nearest star remains 4 light-years away. The beginning of interstellar space is roughly 100 times closer, and a serious engineering plan for reaching it already exists on paper. What follows that plan into the actual void of interstellar space will be something far smaller and far faster than any probe or rocket could carry. The first human-made object to reach another star will arrive as a speck of engineered material traveling at 60,000 kilometers per second. It will not slow down. It will pass through the Alpha Centauri system in hours and continue into the dark beyond. There will be no landing, no orbit, no sample collection, no return. A few grams of cameras, sensors, and transmitters, carried on a sail the size of a kitchen table, flung across 4 light-years by lasers, will execute a flyby at 20% of the speed of light and spend 4 years sending its observations home before the first signal reaches Earth. The people who funded and built the mission will be about 24 years older when they receive the first data. This is Breakthrough Starshot's realistic, best-case outcome, and it is genuinely extraordinary. Humanity will have placed instruments at another star. The system will be mapped, however briefly, by something we made. If planets exist there, the probe will have detected them. If any of those planets carry atmospheric chemistry worth noting, perhaps a hint of water vapor or oxygen or methane, the signal will carry that information home at the speed of light across 4 years of travel. Those 4 years of waiting for the light to cross the gap will be among the more unusual periods in human scientific history. The data is already on its way, already encoded in photons moving at the cosmic speed limit, and there is nothing to do but wait. When it arrives, it will be a few seconds of compressed transmission from something weighing grams that passed through a solar system billions of kilometers wide in a matter of hours. It is the kind of achievement that would mark a permanent line in the history of exploration, and then the gap between what it accomplished and what a human presence would require becomes visible in its full scale. The probe weighs a few grams. A crewed ship capable of sustaining 10,000 people for decades would weigh something in the range of millions of tons. Laser power required to accelerate mass scales directly with that mass. The 100 gigawatts of laser power designed to push a gram-scale sail would need to be multiplied by a factor so large it becomes meaningless as an engineering number. A crewed ship must also decelerate at the destination, a problem the Starshot probe simply ignores by flying straight through. Decelerating a massive ship at the target system requires either a mirror array already in place there to reflect the Earth-based laser back, or an onboard propellant supply to fire engines in reverse, and both options require either prior infrastructure at a place no human or probe has ever been, or carrying the fuel mass discussed in the chapters on the relativistic fuel catastrophe. Breakthrough Starshot will tell us something real about the nearest star, if it is ever built. It will not tell us what it feels like to stand under an alien sky. It will not establish a colony, answer a distress call, or make any decision a human mind would need to make in the presence of something entirely new. It is a snapshot from a passing vehicle. The difference between that and human presence is the same difference that separates a photograph of a city from living in it. Whether that difference is worth the cost of everything interstellar human travel requires is the question. The story has been building toward from the beginning. The rational case for sending only machines to other stars is almost overwhelming. Robots do not need food or water or breathable air. They do not experience isolation or grief or fear. They require no rotating habitat for bone health, no genetic diversity for long-term viability, no social engineering for multi-generational coherence. A gram-scale probe can carry camera arrays, spectrometers, magnetometers, and communication systems, all within a mass budget that makes human life support requirements look comically extravagant by comparison. The scientific return per kilogram of spacecraft is immeasurably greater for a robotic mission than for a crewed one. Every engineering challenge that makes crude interstellar travel staggering in its complexity becomes straightforward when you remove the human passengers. The case for humans rests on something harder to defend in an engineering document. There is a difference between measuring an atmosphere and breathing it. There is a difference between transmitting images of an alien shoreline and standing on it, feeling whatever passes for gravity under your feet, hearing whatever the atmosphere carries. A spectrometer can report the molecular composition of a place. A human being can report what a place is, in the sense that the word is carries when spoken by someone standing inside an experience, rather than analyzing data from outside it. Whether that difference justifies the cost depends entirely on what you think exploration is for. If exploration is data acquisition, then robotic probes are superior to humans in almost every measurable way. If exploration is the extension of human presence and human consciousness into new territories, then a probe that records and transmits is not exploration in any meaningful sense. It is reconnaissance. The history of exploration on this planet runs on both threads simultaneously. Ships sent ahead without crew have gathered intelligence. Since the earliest seafaring, unmanned vessels have charted coasts, mapped hazards, and returned with information that made later human journeys possible. And human expeditions have followed because people needed to be there, to claim, to settle, to transform a coordinate on a map into a place where humans lived, regardless of what machines had already mapped. The scientific return of the Apollo missions was genuinely valuable, but the reason those missions were funded, completed, and remembered for generations had as much to do with what it meant for human beings to stand on the moon as with any specific set of geological measurements. The rocks were secondary, the footprints were the point. The question for interstellar travel is whether that instinct is meaningful at the scales required. An Apollo mission lasted 12 days. A crewed interstellar mission lasts years or decades or generations. The cost in engineering, resources, and human life is proportionally greater. The data a robotic probe gathers will be available on Earth before any crewed mission could arrive. The colonists on a generation ship will, in some meaningful sense, arrive later and know less about their destination than the people who never left home. What they will have is presence. Whether presence, in the fullest human sense of that word, is worth what it costs to deliver it to another star, is not a question with a scientific answer. It is the question underneath every funding debate and every engineering priority in the field. And somewhere inside the honest answer to it lives the realistic upper limit of what this civilization could actually reach. Assemble the pieces accumulated across every chapter of this documentary, and the picture that emerges is specific enough to be useful. Chemical rockets, today, deliver humans to Mars and back with significant risk and no capability for anything beyond the inner solar system. That is a genuine achievement and also a hard ceiling. Nowhere beyond the inner solar system is reachable by any chemical propulsion system within a time frame a human lifetime can accommodate. Nuclear thermal propulsion, validated by test results from more than 50 years ago and repeatedly cancelled before any flight, could halve transit times within the solar system and make the outer planets and their moons realistic destinations within a human lifetime rather than a multi-generational project. A mission to Jupiter's moon Europa, currently a journey measured in years with chemical propulsion, could become a mission measured in months. Saturn and its system, including Titan with its dense atmosphere and liquid hydrocarbon lakes, could enter range for crewed exploration, rather than remaining the exclusive territory of robotic landers. Whether any of this happens depends on political decisions, not physics. If it is built, human reach extends meaningfully outward. If it continues to be cancelled, human reach stays where it is. Nuclear pulse propulsion sits at the boundary between the achievable and the extraordinary. The ships Freeman Dyson's team designed in 1958 and 1959 would have been capable of velocities between 3 and 10% of the speed of light. At 10% light speed, the nearest stellar system is a 42-year journey, one human lifetime, roughly for one of the most extraordinary things a civilization could attempt. The crew that went would know, with certainty, that they were leaving permanently. No generation that funded the mission would live to receive a signal back. The people who arrived would step out under alien light and would be, by any meaningful definition, the first citizens of somewhere other than Earth. The physics have never been questioned. The barriers to building such a ship are legal, political, and institutional rather than scientific or engineering based, which makes them simultaneously more tractable and less predictable than physics barriers. Fusion propulsion sits one rung above that, dependent on demonstrating net positive fusion at engineering scales before any propulsion application becomes realistic. The National Ignition Facility achieved fusion ignition in December 2022, producing more fusion energy out than laser energy in for the first time in history. The gap between that milestone and a sustained, self-powered fusion reactor, let alone a rocket engine, remains measured in decades. Nobody honest has a more specific timeline than that. Everything above nuclear pulse and fusion requires a breakthrough in areas where no timeline is predictable. These possibilities are real in principle. A civilization 100 years more advanced than ours might command any of them. Whether our civilization becomes that civilization within the next century depends on decisions and investments and discoveries that have not yet been made. The maximum realistic human reach within the next 100 years, assuming political will catches up to physics, Mars, the outer planets, possibly the moons of the giant planets as long-duration crewed destinations, with a specific decision to revive nuclear pulse propulsion, the inner edge of the nearest stellar neighborhood within a single human lifetime, barely, at enormous cost, and under every biological and psychological hardship described in the preceding chapters. The rest is physics waiting for engineering, and engineering waiting for a civilization ready to attempt it. Imagine, for the purpose of this final thought experiment, that every problem described in this documentary was solved, fusion propulsion perfected, and delivering specific impulses 10,000 times better than chemical rockets. Radiation shielded by powered magnetic fields, sustained by the fusion reactor itself. Artificial gravity standard in every crewed section. Torpor cycles validated and safe for multi-year use. A generation ship carrying tens of thousands of people under a social architecture adaptive enough to maintain civilization for centuries. All of it working, all at once. What does the universe actually look like from inside that ship? The relativistic table from the chapter on constant acceleration comes back into view. The Pleiades star cluster, visible to the naked eye on any clear winter night, at about 444 light-years, reaches in under 12 years of traveler time. Biologically, a person who boards that ship at 30 steps out onto a world in a foreign stellar cluster before turning 43. Every person they ever knew on Earth has been dead for centuries. The language they grew up speaking has had 400 years to change. The civilization that built the ship is 400 years past the moment of launch. If they managed to transmit a message back on arrival, the reply would reach them, assuming any civilization on Earth still had the technology or inclination to send one. After another 4 centuries of waiting, the galactic center, the hub of the galaxy's spiral arms, and the site of a black hole with a mass 4 million times our star, sits about 26,000 light-years away. A fusion-powered ship at meaningful fractions of light speed gets there in under 20 years of traveler time. Earth ages 26,000 years. The last ice age on Earth ended roughly 12,000 years ago. The traveler departs a world with smartphones and arrives, biologically in their early 50s, at the hub of the galaxy, while Earth ages through a span twice as long as all of recorded human history. They would be the only person alive who remembered what that civilization looked like. They would have no way to describe it to anyone because the language they grew up speaking would have had 26,000 years to become something unrecognizable. Andromeda, 2.5 million light-years away, under 30 years of traveler time, while Earth ages 2.5 million years. Our species is roughly 300,000 years old. The traveler returns to a world that has had 8 times the entire evolutionary history of our species to change, adapt, evolve, or go silent entirely. The asymmetry between traveler time and Earth time is not a side effect of relativistic travel. It is the central and unavoidable fact of it. Go there fast enough to survive the trip, and you return to a world that has aged entirely past recognition. The two descriptions are inseparable. At the scales that make journeys survivable, they become the same fact stated from two directions. You can get there in a lifetime, and by the time anyone who knows you hears back from you, the world they lived in is gone. This is not a failure of the physics. It is an accurate and complete description of what the physics permits. Here is the honest answer to the question this documentary has been building toward from its opening line. What current technology allows, right now, without any new science, Mars, and with difficulty, the inner edge of the outer solar system? That is the real ceiling of human travel in a single lifetime today. It is not a distant star. It is a neighboring planet 9 months away, with radiation exposure approaching safety limits, and a body that deteriorates throughout the journey. The extraordinary achievement of getting there does not diminish how far it is from anything that could be called leaving the solar neighborhood. What the next century could plausibly build, given political will and sustained investment. A nuclear pulse ship carrying enough people to sustain genetic viability, shielded against radiation by mass and active fields, fitted with rotating habitats for bone health and torpor systems for psychological relief, could push toward the nearest stellar system and arrive within a human lifetime. Roughly 40 years. The nearest star. One destination at enormous cost, requiring every propulsion and biological solution described in this documentary to work simultaneously at scales none of them have yet been tested at. The people who arrived would never return. The signal they sent home would take 4 years to arrive. Nobody who funded the mission would be alive to receive it. And yet, that mission, if it ever happened, would be among the most significant things our species had ever done. What physics permits in principle, if energy were limitless and engineering were perfect, the entire observable universe in 45 years of the traveler's experienced time. Every galaxy, every photon that has ever reached a human telescope, theoretically accessible before a traveler born at launch reached old age. The equations are correct. The fuel required exceeds the total mass of the observable universe many times over. The 45-year universe is a real fact about the physics of motion, and it will remain unreachable for as long as our civilization exists in anything resembling its current form. The gap between what physics permits and what we can build is not a gap in knowledge. The equations are known and verified by atomic clocks on airplanes, by navigation satellites correcting their timekeeping every day, by every positioning signal that has ever guided a car through an intersection. It is a gap in energy, the most fundamental currency in the universe, and closing it requires either a civilization with resources several orders of magnitude beyond ours, or a willingness to send people who will never return to a place no one alive will ever see at the absolute limit of what we can build. That is the real answer to the question in the title, and it is both smaller and larger than most people expect. Smaller, because the stars that look reachable from here are genuinely out of reach within the next 100 years for anything carrying human life. The nearest one, on the best technology this century could plausibly build, is a one-way trip of roughly 40 years for a crew that will never communicate in real time with anyone who remembers them. Larger, because physics has placed no ceiling on where the human body can ultimately go, only on how much energy it will cost to send it there. The universe is not closed to us. It is simply vast beyond current reckoning, and we have only just figured out where the door is.